Okay, Assalamu alaikum everybody. Today we will hopefully finish chapter 28. Yes, chapter 28. And so remember last time we mentioned that if the velocity has a component perpendicular and a component that is parallel to the magnetic field, then the particle will follow a helical path. Okay? So the centripetal force will only be due to the perpendicular component. So it will only be due to the perpendicular component. However, the parallel component of the velocity will cause it to still move with a constant velocity in this case in the upward direction. So it will follow a helical path. Okay. And from this, we said the aurora is, or what we refer to as the Van Allen radiation belts. These are usually charged particles that are trapped in the Earth's magnetic field, and so they keep spiraling back and forth around the Earth, and they do not reach the Earth's surface. Okay. And so you can see here, this is the Earth magnetic field. Obviously, it's going from, yes, so these are the magnetic field lines, and these are the charged particles, whether they're electrons or heavy ions or protons, that are circling from one pole to the other. And what happens when they reach close to the atmosphere, they start interacting with the molecules of the atmosphere, and I excite these molecules or atoms. And when they get excited to higher energy, and when they go back to the original state or the ground state, they will emit a light. Okay, and that's what causes the northern lights. So, for example, here we're showing at an altitude of about 500 kilometers. You have electrons interacting, for example, with oxygen atom, and they emit green light. Okay. At lower altitudes, you can have, for example, nitrogen, and when an electron interacts with the nitrogen, it excites the nitrogen atom, and when it relaxes back to the ground state, it emits a red light. So that's why we see basically a spectrum of light: green, blue, and red. A very beautiful northern light. So in the northern pole, they are called the aurora borealis, and in the southern pole they are called the aurora australis. These are the I guess the Latin word for the northern and southern lights. Okay. So this is what where we stopped at last time, and now we're going to start a new section. So let me go to the presentation mode. Okay, so let's assume we have both an electric and magnetic field. They are both are present, and as shown here, we have an electric field in the minus y direction, and we have a magnetic field in the minus z direction. And let's assume we have a positive charge, and it has a velocity in the positive x direction. Okay, so first of all, electric field. When a positive charge is an electric field, it will experience an electrostatic force or electric force. So the first thing is the charge will be subjected to this force, and since it's a positive charge, the force and the electric field are in the same direction. And remember, the force in that case is given by QE. But that's not the only force acting. There is also the magnetic force. So if we use the right hand rule, okay, so if we point the index finger in the direction of the velocity vector, first vector, and the middle finger in the direction of the magnetic field vector B, then there will be another force, FB, that is upward, that is in the positive y direction. So this is the second force that is acting. So you can see this moving charge is influenced by two forces. Let's ignore the gravitation force because it's negligible compared to the electric and magnetic forces. Okay, and we know the force is given by Q, V crossed with B. So now we have two forces acting. So we have the electrostatic force, Fe, let's say this is Fe plus Fb. Okay, so these are two forces acting, and obviously they will influence the path of the charge. Okay, if we take a look and we from this side, and we can display the same thing. So here we're showing the velocity vector is to the positive x-axis. Okay, the magnetic field vector is into the page in the minus z direction, and the electric field vector is in the minus y direction. So again, we're representing this force here. This is the electric force. This force is represented like this. So you can have a plot where you have a three-dimensional Cartesian coordinate, or you can have just a view from one angle. Okay, so here we're looking from this angle, which is as if you're placed in the positive z axis and you're looking at the geometry. Okay, so obviously you can see that if the forces are equal, if the electric force and the magnetic force are equal, they will cancel each other in this case, and the particle will move in a straight path. If it has an initial velocity, okay, it will continue moving with the initial Newton's first law. If a particle or an object is moving at a constant velocity v, and the sum of the forces is equal to 0, then it will continue moving at the same velocity. Okay, but if the forces are not equal, obviously the particle will change direction. Okay, so this is here. Let's assume the first situation, the two forces are equal. Okay, then the particle will just follow a straight path. Okay, so this is a situation. So in that case, we can say that in order for this to take place, we can say that Q V crossed with B, the magnitude of this force should be equal to the magnitude of the electrostatic force QE. Okay, or since here V and B are perpendicular to each other, we can say that QVB is equal to QE, and so the Q's will cancel, and you can see V is going to be in this case E over B. Okay, so this will take place if the velocity or the speed of the particle is equal to the ratio of the magnitude of the electric field divided by the magnitude of the B field. In that case, the particle will just move in a straight path. Okay, so now if the forces are not equal, they do not cancel each other. Okay, and then there will be a deflection. So this is another case. So here we are assuming that the electrostatic force is larger than the magnetic force. Okay, so this force is larger, so we expect the particle will bend, so it will move in this path. So because the electric force is larger, and vice versa. If the magnetic force is larger than the electric force, then the particle will deflect in the other direction. So there are many devices that are based on a movement of charged particles in the presence of both electric and magnetic fields, and these are used today in hospitals, in research facilities, and so on. We'll speak about some of them. Okay, so let's speak about the first one. We already mentioned that when the magnitude of the two fields are chosen so that QE is equal to QVB, the forces, they will cancel. Okay, so if you have, in this case, you have an electric field moving from the positive plate to the negative plate. So this is the electric field here, E. Okay, and if you have a magnetic field in this case, it's into the page, so it's a minus Z direction. Let's assume we have an electron gun or a charged particle. So here the charged particle will be moving in this direction. Okay, and so it will be subjected to an electric force and the magnetic force in opposite direction. And if you satisfy this condition, then the particle will just move in a straight path. So it will follow a straight path. This is called the velocity selector. So if the velocity does not satisfy this condition, it will either deflect this way or it will deflect this way, and it will not reach a target. Let's assume you have a target here that you're bombarding with electrons or with protons. And so you have a velocity selector, so the target will only be hit with when the electron or the proton has a certain velocity. So if it has a certain velocity, that means it has a certain fixed kinetic energy. And so if V, now we said V is equal to E over B. Okay, that means the kinetic energy of the particles that will hit the target here will have a kinetic energy of 1/2 mv squared, and so this is E squared over B squared. So by using this device, basically you are selecting what's the kinetic energy of the charged particles that will hit my target. Okay, and obviously there are important reasons for why we want to select a certain kinetic energy in order to hit a target. So this is called a velocity selector, and this is just based on electric and magnetic field. So again, the total force is equal to the electric force plus the magnetic force, and if the magnetic field is perpendicular to the electric field and the magnetic field is perpendicular to the velocity vector as illustrated here. Okay, so first of all, the electric field is perpendicular to magnetic field. You can see the electric field is in the x direction and the magnetic field is in the minus z direction, but also the velocity is perpendicular to the magnetic field. The velocity is in the positive y direction, and the magnetic field is in the minus z direction. So if the total force is equal to 0, that will be our velocity selector. V is going to be E over B. Okay. All right, so this is one device. We can use a velocity selector and we add to it another component to build a bridge mass spectrometer. Mass spectrometer is a device that is used in labs, research facilities, and so on in order to determine the mass of heavy ions or basically charged particles. Okay, so here we have a velocity selector. This part is a velocity selector. Okay, so if V is E over B, the particle will move in a straight path. Then it will enter this region. This region has a constant magnetic field, and you can see that it's not necessarily equal to this one. So it can be different from this magnetic field. When it enters this magnetic field, it will move, it will experience, so in this region, it will experience a centripetal force. Okay, and it will move into a circular or semicircular path in this case. Okay, so here, and it will hit a point P here. Okay, and usually you have a fluorescent screen. So I know when it hits here, we can measure the distance and we can determine what is this distance x or 2r. So we can determine, and by doing that, we can determine what is the mass of the ion. So let's look at the equations. So remember from before, we said the electrostatic force, the magnetic force is QVB is equal mass times the acceleration, which is V squared over R. And from this, we obtained that R is equal mv. So this is the mass of the ion or the charged particle times the velocity. So this is the velocity that is selected, divided by Q and B0. Remember, B0 is the magnetic field magnitude in this region. Okay, so we can see that the mass divided by the charge is equal to the radius. So the radius is this radius here, R, times the magnetic field strength, B0, inside this region, divided by V. Since V is equal E over B, this is the velocity selector, we can write that the mass divided by the charge of this charged particle is given by R times B0, which is the magnetic field in this region, times Bn, this is the magnetic field that is in this velocity selector, divided by E. So here we just replaced V, so we replaced V by E over Bn. So R you can measure in this spectrometer. Stay with me, Ibrahim. Okay, and B0 and Bn are known. Okay, so these are magnetic fields that we can set. and the electric field is known. So by using this instrument, we can actually determine the mass divided by the charge. The mass divided by the charge of these ions. Obviously, if we determine the mass divided by the charge, we will be able to identify which charged particle is this. Okay, because a charge of an ion is going to be only a multiple of E. Okay, and so if we know, we can basically determine M over Q. So this is a mass spectrometer. This instrument is called the mass spectrometer. It's an expensive instrument that is used in research facilities and chemistry labs and so on. Okay. The other very common device that is built on the presence of the electric field and magnetic field is the cathode ray tube. The cathode ray tube is a simplified version of the Joseph John Thomson experimental apparatus that led to the discovery of the electron. This was done in 1897, and Joseph Thomson obtained the Nobel Prize in physics in 1906 because of this finding, using the cathode ray tube in order to verify or to the discovery of the electron. So this device here is based on, you establish a voltage, so you have a delta V here, and you pass a current through a filament. This filament is usually a tungsten filament. So the electrons gain enough energy, and if you subject them to high potential, so this is, let's assume this is connected to ground, let's assume this is 0 voltage here, and this is a very high positive voltage, the electron will be accelerated. Because there is a potential difference, it will be accelerated. We can determine the velocity because we know delta K plus delta U is equal to 0. So we can determine if the electron, we assume they started at a 0 initial velocity, we can determine what is the velocity of the electron when it enters the cathode ray tube. Okay, so this electron will, if there is no electric field or magnetic field, it will just continue moving in a straight path. Okay, so it will hit this fluorescent screen, and it will create, you will see a bright spot in the middle of the television screen. Okay, now if we add an electric field, so let's assume we add an electric field. So here, this is a positive plate, this is a negative plate, so we have an electric field like this. Okay, since the electron is negatively charged, the electrons will experience a force in the opposite direction. So the electron will deflect and will hit a different point on the cathode ray tube. Okay, so this is an electric field, and okay, now let's add also a magnetic field. So we determined that this is the electric force. Okay, the magnetic field, if we use QVB, if we do the right hand rule, so V is in this direction, B is into the page. The magnetic force is, since this is a negative charge, it's not going to be up. So up is what we get with the right hand rule. Because of a negative charge, it's going to be down. So this is electric force. The electron will also be subjected to a magnetic force. Okay, so if you control the strength of the electric field and the strength of the magnetic field, the electric field will move the electron, and so you'll be able to move the position of the electron in this direction. Okay, so up or down depending on the strength of the electric and magnetic forces. Okay, so this is another schematic diagram. It's showing, so first of all, this glass bulb is evacuated. In other words, there is vacuum inside it, so the electrons does not hit molecules when it's flowing. Okay, this is the electron gun. The electrons are coming through these two slits, and they experience a very high voltage, okay, between the cathode and the anode. So they are accelerated with a certain velocity v, and then they move between the two plates, which is the two electrodes that are causing the electric field. The electric field is going to be from the positive to the negative plate, and you have two coils that are parallel to each other. We will see how coils generate magnetic field. So this is a magnetic field. You can control the strength of the magnetic field by controlling the current through these coils, and you can control the strength of the electric field by controlling the voltage between the two plates. And so you can deflect. And this was the principle of the television the original television, basically you have an electron that is scanning over the screen at a very fast rate and generating an image, black and white image at that time, okay? And that's what they used to use before inventing the flat panel screens. So when I was young, the first television, they used to have cathode ray tubes like this, and so we obviously it's scanning at a very fast rate. You only see an image, you do not see the individual electrons. But if you have these are really electrons hitting the fluorescent screen and generating the image. Okay, so let's see how Thomson determined the mass over the charge of an electron in 1897. So first of all, if he has an electron flowing at this constant velocity, let's assume we have an electron gun and you have a potential difference and you're accelerating the electron, okay? Originally, the electric field and magnetic fields are zero, so let's assume we have the velocity of the electron, okay? The next is we're going to establish an electric field. If we establish the electric field, the electrons, because it's a negative charge, so the force is going to be in this direction, it will deflect upward. We can determine the amount of deflection y by using the equations of motion at constant acceleration. In this case, we have a constant force acting on the electron, and we can determine the force is QE. If I determine the force, I can determine the acceleration. The acceleration is force is equal to ma. So the acceleration is, so this is what we did. So force is equal to QE is equal to ma. We can determine the acceleration, and since we determine the acceleration, we can determine the deflection y. Y is equal y0 plus v0t plus 1/2 at squared. Okay, so this is, but because x0, let's assume x0 is y0 is 0 here in the middle of the screen, okay, and the initial velocity in the y direction is 0, v in the y direction, v0 y is 0, v0 y is 0, so we end up, so this is really plus x y0 plus v0 yt, but because this is 0 and this is 0, it simplifies to just 1/2 at squared. Okay, so now we know the deflection y, and if we replace the time it takes for the electron to hit the screen, I can determine that because I have the velocity in the x direction. This is velocity in the x direction. I have the length of my cathode ray tube. I can determine, we know v is equal L over T, so T is going to be equal L over V. Okay, that's what we have done here. We replace T by L over V. Okay, so I have L, I assume we have V, but we don't have Q over M. We have E because the electric field, we're using parallel plates. Okay, now what we're going to do, and this is what Thomson did, he applied the magnetic field. Okay, so this is this is an equation. From this we get V squared. This is V squared. Okay, let's now apply the magnetic field. So now we have, besides we turn off the we turn on the magnetic field, and we increase the magnetic field until the electron comes back to the middle of the screen. Remember, it has deflected by amount y. Okay, when I turn on the magnetic field, I increase the magnitude until the electron comes back to the middle of the screen. Okay, when I achieve that, that means now I have a velocity selector because the electric force and the magnetic force cancel each other. Okay, so FB is equal to FE in magnitude, and I can write FB is QVB, FE is QE, so the Q's will cancel and I obtain V is equal E over B. Okay, so I take the square of this and make it equal to this. So this is what we are doing. E over B squared is equal to V squared, which is 1/2 Q over QE over M times L squared divided by Y. Y you measure, because you can measure from the middle of the screen to the top of deflection, and you can rearrange the terms of this equation and determine the mass over the charge. So Thomson, basically he was the first one to measure the mass over the charge of an electron. Okay, at that time they knew the elementary charge. Okay, the experiment that we described before, who was it? I forgot now. Okay, which is having drops charged and going through an electric field. So measuring the velocity, they determine the charge is quantized, is always a multiple of a certain number E. In this experiment, they determined the mass over the charge of the electron. Okay, so M over Q is given by B squared, which we know the magnetic field. We know the length of the cathode ray tube divided by 2 E, the potential, the electric field strength, which is equal to delta V over the distance. And if this distance here is D, E is just equal delta V over D. Okay, and we know the deflection Y, so by plugging the numbers, we can determine the mass divided by the charge of an electron. So it looks a simple experiment, but this was an invention. This led to a Nobel Prize. This led to the discovery of the electron. So the mass of the divided by the charge of the electron. All right. This is another device. This is a device that is available in hospitals. So, for example, Al-Ain Hospital, they have this cyclotron. Okay. The cyclotron uses both electric and magnetic field. Ibrahim, you either go make wudu or واحد. And I don't want to see somebody sleeping in my class, please. Okay. So, a cyclotron is a particle accelerator. It was invented by Ernest Lawrence, and he obtained a Nobel Prize for this one. So this is another Nobel Prize device. Okay, and this device basically, you can use it to accelerate the charged particles. So what you do, let me explain the principle of this device. So follow me, please, because this is not a simple one. So basically, in the middle, you inject a charged particle. It can be a proton, a heavy ion, or even an electron. Okay, these are two Ds. It's called a D because it has a shape of a D. Okay, so they have one D here and one D here. Okay, when you inject the particle between the two Ds, we establish an electric field. So there is an electric field. You see, this is here the voltage between the two Ds. Okay. So the charged particle will accelerate, but when it reaches the inside of the D, inside the D there is only magnetic field. There is no electric field because the electric field is only established in the space between them. Okay, so it experiences an acceleration. So let me draw it here. So the charged particle experiences an electric field and it will accelerate, but once it reaches the D, there is only a magnetic field there, and a magnetic field there will be a centripetal force, so it will move in a circle. Okay, then it reaches here, the polarity is reversed of the electric field and it gets accelerated again. Okay, then when it gets accelerated, it moves in a larger circle. It gets accelerated again, then it moves in a larger circle, and so on. So it keeps doing this. So here it gets accelerated, it moves in a circular path. Then it gets accelerated, it moves in a larger circular path because velocity increased. Then it gets accelerated and it moves in another circular path. So it keeps doing that until it reaches the largest radius. And when it reaches the largest radius, it has a certain kinetic energy, a certain velocity, these charged particles, and we can use them to bombard whatever we want. So, for example, the people who have cancer, they can inject, for example, in the bloodstream some radioactive materials, and they can image these radioactive materials using either a gamma camera or a positron emission tomography machine. In order to do that, they need to produce these radioactive pharmaceuticals. The way they produce them, they put the chemical, originally it's not radioactive, but they put it in front of the beam. So for example, this is a proton beam. Let's assume this is a proton beam. When you put the vial with the radiochemical in front of the beam and the protons bombard this radiochemical, it becomes radioactive. Okay? It becomes radioactive. They can transport it to the hospital. They inject it in the bloodstream of the patient, and they can do the imaging. So the cyclotron is a very useful device. And for example, one major machine that is positron emission tomography that is used to determine the spread of the cancer. So if you image the cancer with a CT machine, you can see a little bit the contour of the tumor. But the microscopic disease, the spread of the cancer cells, you cannot see it. But if you inject in the bloodstream positron emitter, which is, for example, one of the radiochemicals is called FDG, which is fluorine and deoxyglucose. It emits positrons. The cancer cells, they consume a lot of glucose. So when they take up this radiopharmaceutical compared to the normal cells, they become very apparent in the image. And so we can see not only the gross tumor, but we can also see the microscopic disease around the tumor using these positron emitters. So it is a very important device that is used for diagnosing the extent and the spread of the cancer in patients, and we would not be able to do that if we did not have a cyclotron in order to produce these radiopharmaceuticals. Okay, so obviously the principle of conservation of energy, if you want to determine the kinetic energy, the final kinetic energy, okay, so every time the particle passes between the two Ds, it has an increase in kinetic energy, which is equal Q delta V, because we have a potential delta V. So every time it passes, so the first time you will have Q delta V. The second time it passes, you will have 2 Q delta V. The third time it passes, you have 3 Q delta V. So it keeps going. So if you have 1,000 times it's going through 1,000 times between the two Ds, you can reach 1,000 Q delta V. So you can reach very high kinetic energies, very high velocities, and when you hit the molecules of a radiopharmaceutical, it becomes radioactive. Okay. So inside there is a centripetal force due to the magnetic field, and we can always write F is equal to QVB, which is mv squared over R. We can determine V over R is equal to QB over M. What is V over R? Remember, it's the angular velocity. Remember, V is omega R. So omega, this is what we call the cyclotron frequency. It's really radial frequency. V over R is equal to the charge, for example, a proton, which is E, times the strength of the magnetic field B divided by the mass of the proton. So you can see that actually the frequency is constant. In other words, since omega is constant, it's just determined by the charge of the proton divided by the mass of the proton times the magnetic field. Omega is constant, and omega is 2 pi f. So omega is 2 pi f. Omega is 2 pi f, which is 2 pi over t. That means the time it takes for the proton to move a full circle here is constant. So even though it's moving from a smaller circle to a larger circle and so on, the time it takes for one full revolution is the same. This is very important, otherwise you will not be able to sync with this electric field. If it's not constant, that means this electric field frequency or periodicity has to change. Okay, so we are able to do it for protons because we can sync. Unfortunately, for electrons, you cannot do that because they quickly reach speeds that are close to the speed of light, and the mass started to change. If you study relativity, the mass, when you reach these particles, when they reach close to the speed of light, or the mass changes, and then you lose because there is m. This mass at the relativistic speed starts changing, so becomes this frequency is not constant anymore, okay, and you lose the sync. But they came up with a device that actually changes the frequency of this electric field, and they call it the synchrocyclotron. Synchronized cyclotron. That's a new invention, or another invention. Okay, so this is the frequency of the velocity increases every time the particle passes between the Ds, but the angular velocity omega does not change. That's important. Hence the frequency of the square wave. This is the frequency here. This is so this is with a period, one cycle, okay, and the frequency just equal 1 over the period. So it's equal omega over 2 pi, which is QB over 2 pi m. So you can see it only depends on the strength of the magnetic field, because Q over M is constant, hopefully, is constant, if the particle does not reach relativistic speeds. So this is another important device that is used, okay? So we're not speaking about only theory here. We are speaking about actual devices, and there are usually, when you have a cyclotron, you have to have a physicist, you have to have an engineer, you have to have technicians, and so on. So it's a full team that is operating the cyclotron. They call it mini cyclotron, because in the hospital, the mini cyclotron fits about maybe twice the size of this table in diameter. You can see I'm a medical physicist, so I get excited when I describe these devices, because they are very useful. Okay, so what was the question? How did they know? Well, originally, they know the electron is charged particle, so if you subject it to an electric field, it will accelerate. Okay? They found out later that if you subject it to a magnetic field, it will move in a circle. So the genius of the inventor of the cyclotron, which is Ernest Lawrence, when he invented this, I think he was in Stanford University, is he combined these two principles in a very smart way. So he said, what if we have electric field that is switching back and forth, and we release a particle, so it sees an electric field, it gets accelerated. When it reaches inside the D, there is only magnetic field, so it will move in a circular motion. It reaches here, you split, you reverse the polarity of the electric field. It gets accelerated again, okay? So it gains in kinetic energy. Then it moves in a circular path. It gets accelerated. So this is the genius, that he combined these two physics, well, more than two, physics principles to invent this machine. So this is, yes, the idea, how did he, the question is, how did he come up with this idea? I mean, people knew the charged particles get accelerated to electric field, and magnetic field makes them move in a circle. But combining these ideas to come up with something like this, that's not, you need a Nobel Prize winner to do that. Okay? So anyway, so this is, here we're looking at the top view of the cyclotron. So this is much clearer. You can see you reject the protons here, they move, and they move. Every time they cross here, they get accelerated. Then, when they move here, the speed does not change here. It just moves in a circle, so the speed is the same. The speed gains here. So here you have the speed is gained, and so on. Okay? So here I'm just displaying the kinetic energy is 1/2 mv squared. And if you want to determine the kinetic energy of the particle when it leaves the cyclotron, you have to know what is this radius, r, okay? And you can replace, we have V is QB over R, QBR over M, sorry. And the kinetic energy is 1/2 mv squared, so you get what is the kinetic energy of the proton or heavy ions when it exits the cyclotron. Okay, so they exit the cyclotron with a constant kinetic energy. So, for example, 1 mega electron volt, or they can, I don't know how far they can reach in terms of the kinetic energy, but a linear accelerator can reach up to 26 mega electron volt. This machine probably about the same thing. Okay, any question about the devices? Okay, so let's go to the next one. All right, so I will go to the, well, I think this is, for the sake of time, let me go over this. Okay, so this is a checkpoint. We have an electric field that is coming out of the page in the positive Z direction. We have a magnetic field in the minus X direction, okay? And we have different situations for the velocity vector. First situation is in the minus X direction. Second situation is in the plus Y direction. This is in the plus X direction. Third situation, and the fourth situation is in the minus Y direction. Okay, the question is rank 1, 2, 3, and 4. These are the different situations according to the net force on the particle. Greatest first. The net force on the, this is, in this case, it's a charged particle. Okay, so obviously we have to do it step by step. This is not something you just can, right, so we have to do step by step. So first of all, we need to determine the electrostatic force. So the electrostatic force F is equal to QE. Okay, so here, this is the, so since it's a positive charge, the electric field, notice the electric field is in the plus Z direction, so we can, so this is, I can write F is equal QE, so F is equal Q, and E is the magnitude of E, times K, correct? The electric field is outside the page, so it's plus Z direction, so it's K, all right. So now we're going to determine what is the magnetic force. We know the total force is going to be equal to the electric force plus magnetic force. All right, so what's the, let's take a first situation. Okay, so we need to determine what is the magnetic force. What is the magnetic force in the first situation? 0, because the velocity vector and the magnetic field vector are parallel. So a sign of 0 is 0. So FB is equal to 0. That means the total electric, the total force, sorry, is going to be just equal to Q E times K. This is the total force in the first situation. Let's take the second situation. The second situation, we have, so the second situation, we have the velocity vector up, the magnetic field vector to the left. So the force is outside of the page, so it's in the plus K direction. Plus K direction. So we can write FB is equal Q V B times plus Z direction is K. Okay, so what's the total force? The total force is going to be QE, which is electrostatic force, plus QVB times K. Correct? So you know the electric force is QE times K. The magnetic force is QVB times K. So this is the total force. So this is the magnitude. Third situation. In the third situation, we have, what do we have? Magnetic force. 0, because the angle is 180 degrees. Sine of 180 is 0. So FB again is 0. And the total, F total in this case is just Q E times K. Okay, the fourth situation. So in the fourth situation, we have the velocity vector is downwards. So let's go again. Well, it's opposite to the other one, so the force has to be in the other direction, but let's verify it anyway. So this is the velocity vector along my index. Okay, I have to return like this. The middle finger is pointing in the P direction, it's to the left. So the force is into the page, so it's minus K. So we can write FB is minus QVB times K. So what is the total force? The total force is QE, which is the electrostatic force, minus QVB, all of this times K. So the electrostatic force is coming out of the page, but the magnetic force is into the page. They are kind of opposing each other in this case. So this is why we get QE, because it's in the plus K direction, minus QVB, because it's in the minus K direction. Okay, so now we can classify them. Which one has the highest magnitude? 2. So we can see F at 2 is larger. What's next? 1, which is 1. Actually, it's QE. And 1 is equal to 3, because both of them are QE. 1 is equal to 3, okay, which is larger than this one, which is the fourth one. The fourth one is QE minus QVB. صح ولا؟ So larger than F4. So the correct answer in this case is this one. This is a very difficult conceptual question. That's why we did it step by step. This is more difficult than a problem-solving question because you have really to reason and determine what is the electric field, magnetic field, forces, and add them. So these two forces, they are the superposition principle applies, and so you can deal with the electrostatic force on its own. You can deal with the magnetic force in its own, and then just add them. Vector addition. Vector addition. Okay, so this is the result. Okay, so here is another problem. This is a mass spectrometer. Okay, we're given the charge. In this case, I think it's a proton, is it? Well, we're given the charge 1.610 minus 19. We're given x. This is which is equal to 2r. Okay, the diameter of the circular path. Remember, so first of all, the charge is accelerated through the potential difference here, delta V. Okay, it reaches a certain velocity here, constant velocity. Then it will experience a magnetic field, so it will move in a circular path. Okay, and they are giving us x is, which is 2r, is 1.63 meters. The magnetic field is 80 millitesla. The potential is 1000 volts. What is the mass of the ion? And what is the mass in atomic units? Okay, one atomic unit is 1.67 10 minus 27 kilograms. So first of all, we need to determine the mass of the ion. Okay, well, first of all, let me determine the velocity of the ion first. Okay, so we have a potential difference. Let's assume that it starts with an initial velocity 0. And let's assume it reaches a certain velocity v. So I'm going to use conservation of energy, delta k plus delta u is equal to 0. So delta k is 1/2 mv final squared minus 1/2 mv initial squared, which is 0. Okay, and I can take the delta u to the other side. Okay, and since we are interested in magnitudes here, so I will just write q delta v. So this is q delta v. Okay, and I can solve for v. So v is going to be the q delta v times 2, okay, times 2 divided by m square root. So I have the velocity when it reaches here. So now it's going to experience a constant force. So I can write the magnetic force now, which is QVB, since B and V are perpendicular to each other, so I can write this QVB is equal to the mass times the acceleration, which is mv squared over r. Okay, so here they are asking for the mass. So let me try to simplify this. Okay, so the squared will disappear, this will disappear. Okay, and so I have QB is equal mv over r. Let me replace v here. Okay, so let me replace that. So this is going to be equal to m times square root of 2q delta v divided by m. Okay, we don't know m. I did not get the number here because I don't know the mass. Okay, and I still have to divide by r. So now qb is equal m over r square root of q delta v divided by m. And I need to solve for m. So I can write, I take the square of this equation, so it becomes q squared b squared is equal to m squared divided by r squared. Okay, and the square root becomes just 2q delta v divided by m. Okay, so the square will cancel and this q will disappear. Okay, the mass here will simplify and I can solve for m. So I can write m is equal q b squared times r squared divided by 2 delta v, correct? So r is just x over 2, so I can write this q b squared x over 2 squared divided by 2 delta v. I have everything. I have the charge, I have the strength of the magnetic field, I have x, and I have the potential difference, 1000 volts. So now I can solve for m, and it will be in kilograms if I use the SI units. And then I divide this, once I divide, so I divide this by the atomic mass unit, which will be 1.67, 10 to the minus 27. This will give me how many atomic mass units, واضح? So here we use a number of concepts. First of all, we use the acceleration of an electron due to an electric field to reach a certain velocity v here. Then we use the fact that a moving charge will experience, in a magnetic field, will experience a centrifugal force. So we use conservation of energy, concept from 121. We use F is equal to QVB. This is magnetic force. This is the second concept. We use F is equal to MA. This is Newton's second law, third concept. Okay? So then we just solved, and we were able to obtain the equation for the mass. So we used very important three concepts: conservation of energy, acceleration of electron to potential difference, Q delta U is equal to Q delta V. There are four concepts. We use F is equal to QVB, which is magnetic force. It's equal to MA, Newton's second law. And we also use the centrifugal acceleration. A is equal to V squared over R. So this is a nice problem where we have 4 or 5 physics, very important physics concepts. We studied some of them in 121, some of them in 122. And this is how the beauty of physics. When you put things together, magic can happen. This is a spectrometer, a mass spectrometer. All right, next. So the solution is, you get the mass is 3.39, 10 minus 25 kilogram, and when you divide it by the atomic mass units, you get 204 atomic mass units. So now, if you have the atomic mass units, you can determine which ion is this. I don't know, I don't have the table of periodic table with me, but you should be able to find it and determine what ion is this, or what atom nucleus. All right, here is another problem. So this is a different one. An electron, so in this case, an electron has an initial velocity of 12J plus 15K kilometers per second. So remember, this is 10 to the power 3 meters per second. And a constant acceleration. So it has a constant acceleration in the x direction. So 2 10 to the power 12 I meters per second squared in a region of uniform electric field. So we have a uniform electric field and magnetic fields. They are present. We are given the magnetic field is 400 microtesla in the x direction, 400 microtesla in the I times I. And they asked find the electric field. So we have an electric field, magnetic field. We're given the vector, velocity vector. We're given the acceleration vector, and we're given the magnetic field vector. How do you solve this problem? So we have magnetic and electric field acting at the same time. They have given us the acceleration. Immediately when you get acceleration, think about Newton's second law. F is equal to ma. So first of all, we know F has to be equal to ma. But here F is two forces. We have the electrostatic force Fe plus Fb. So I have to write these. What's Fe? Fe is a Q times E, and which we do not have. They asked us to solve for E. And the magnetic force is Q V crossed with B. Okay, so I have the velocity vector, I have the magnetic field vector, I have the acceleration. I should be able to solve for E. So because now I can write mass times acceleration is QE plus QV crossed with B. So I can solve for E. So if I divide by Q both sides, so this is mass divided by Q times acceleration is equal to E plus, and divide by Q, this is V crossed with B. Okay, I can take V crossed with B to the other side and I can solve for E. Notice this is a vector equation. This is mass divided by the charge times the acceleration minus V crossed with B. So now I just replace. Okay, so this is the mass of the electron divided by the charge of the electron, which is minus, so you have to be careful here. So this is minus E, okay, times the acceleration, which is given to us. It's 2 × 10⁻12 I minus V crossed with B. Let's write V. This is 12 × 10⁻3 I plus 15 × 10⁻3 J. This is crossed with V, the velocity, this is V crossed with B, which is 400 10⁻⁶. Let me write it here. So we have a crossed with 400 microtesla 10⁻⁶, and it's I. Okay? Yes. We divided by Q, so the mass over the charge, we get rid of the Q. So we have mass of the charge times the acceleration minus V crossed with B. Okay, so the velocity vector, oh, sorry, thank you. Yeah, you see that you can easily make a mistake between I and J. Huh? So it's J, not I. Thank you. Otherwise you get confused. Okay, so now let's do this. So mass of the electron is 9.11 10⁻31 divided by minus 1.6 10⁻19, okay, times 2 10⁻12 I. Let's do the cross product. We have a minus, so J crossed with I is what? Minus K. So we have minus and minus, so it becomes a plus. 12 10⁻3 times 400 10⁻⁶, and we said this is K. Yeah. Then we have J crossed with I. What? صح, K. Sorry. Yeah, it's good I have you're awake. Okay, so 15 10⁻3 K crossed with I. K crossed with I is what? J. K crossed with I is J. Plus J, yes. So it's since I have a minus, so it's minus 15 10⁻3 times 400 10⁻⁶ J. Okay, so you can see I have an I have a J, and I have a K component. Oops, I lost my pen. Okay, so let's see. Yes, so if you replace the numbers, they come out nice. Minus 11.37 I minus 6J plus 4.8 K volts per meter. And you can determine the magnitude, x squared plus y squared plus z squared, square root of that. So I think we did everything correct. But this is now vector equations. You have to be able to write these equations in vector form and do the math. So basically, writing the equation is not the challenge. This is more a mathematical challenge than a physics challenge. In the previous problem, we used how many concepts? We used maybe 5 concepts of physics. In this one, we just need to write the equation for Fe and Fp and solve. So this is really a math problem, okay? Because we have the vectors and we just need to determine the electric fields. Okay, I still have 15 minutes. Any questions so far? So, using electric field and magnetic fields, we've seen a number of instruments. The velocity selector, the mass spectrometer, the cathode ray tube, which was the television tube, basically, the cyclotron. So these are very important instruments that even nowadays are still being used. Okay? Now, since a charge, when it's moving, it experiences, in a magnetic field, it experiences a force. If we have a number of charges moving, each one of them will be experiencing a force. If we have a current flowing, These are number of charges flowing. Each one of them is going to be experiencing a force. That means the wire will be experiencing a magnetic force. Because we know the current is a flow of charges. And we know the velocity of the charges, the average velocity is what did you call it? VD, which is the drift velocity of the charges. We determined before VD. So if I know VD, if I know the current, and I can determine VD, I can determine, and if I know the number of charges per unit volume, I can determine how much is the force on this wire. Okay, so this is a new concept. You have seen the concept of charge moving, it will experience a magnetic force if it's moving in a magnetic field. Same thing, a wire that has a current, if the wire has a current flowing through it, it will also experience a magnetic force. And this is our next topic. Okay, so this is here a wire. Originally it has no current, and the magnetic field is, we have a constant magnetic field outside the page, which is in the plus Z direction, so it will not experience a force. As soon as you pass the current through it, if you pass a current in this direction, in the plus Y direction or upward, it will experience a force in this direction. I lost my pen, unfortunately. Let me see. Yeah. Try something. Now I have 2 pens. No. Yeah, none of them works. Okay, never mind. Okay, for the sake of time, I will just explain. So here, you can see that this wire will experience a force to the right. If you reverse the direction of the current, this is an experiment you can perform. You can pass a current in a wire and put it in you can bring just a regular magnet, a strong magnet, and put it close to the wire. You will see the wire moving due to the magnetic force. Okay, so this is the equation. If you have a wire of length L, we can define what we call the length vector L. Okay, the length vector is a vector in the same direction as the length of the wire, and we multiply, so we can use, so it has the magnitude of the length of the wire, and it is in the direction of the current. So L is a length vector, a magnitude, the length of the wire, and the direction is along the wire segment in the direction of the current. If we define this vector, and this is the magnetic field vector, the wire will experience a force that is given by the current I times the length vector L crossed with the vector B. So this is another equation where we have a cross product, but instead of QVB in the previous equation for a single charge, you have V crossed with B. In this case, it's I, which is the current, and L, which is the length vector, crossed with the magnetic field vector B. And if you want to determine again the direction of the force, you use the right hand rule. So you point the first vector L along your middle finger, the magnetic field vector, which is the second vector, along the this is the index, the second vector along the middle finger. The force will be on the given by the thumb. So this is the right hand rule, so you can use it in order to determine the force. Okay, so it doesn't matter if you think about current as moving positive charges or the opposite of negative charge. You will have the force move in the same direction. Okay, let's take the first case. Let's assume the current are positive charges moving. Let's assume the current is positive charges moving down. Okay, and let's use the right hand rule. So in this case, the magnetic field is out of the page. Okay, and the velocity vector is down. So let's do that. Okay, so the velocity vector, here. The velocity vector is down, and yes, velocity vector is down. Magnetic field vector is out of the page. The force is going to the left. So this is the thumb. So the force is to the left. Let's check if we think about the current as the opposite direction of negative charges. So here, instead of positive charge moving down, if we think about it as electrons moving up, okay, and we do the right-hand rule again, okay? So let's do the right-hand rule. So this is V, the velocity vector is up, magnetic field vector is outside of the page, okay? Now, the thumb is giving this direction, but it's a negative charge. So I have to reverse, flip the direction. So this is so in both cases, whether you think as current as a flow of positive charges or the opposite of the flow of negative charges, you get the same direction of the force. Okay? So, now let me quickly, oops, I don't know what's happening to my computer today. All right. So you know what? I like to go back to the display mode. Okay, this is just a derivation of that equation, and it's not a difficult derivation. It's a simple derivation. If you remember the current, the relationship between the current and the drift velocity v, we said the current is Avogadro's number is Q Vd times the cross-sectional area A times. Let me switch this. Okay, so we know for a single charge the force is Q Vb crossed with B, Q Vd, which is the drift velocity of the charge in this case. Okay, let's assume we have a certain volume of the wire, and the volume is given by the cross-sectional area times the length. So we're considering this part of the wire. This is the volume. Let's determine the number of free charges in this volume, free carriers, charge carriers. So the number of charges in the segment, in this segment L, is given by the volume, which is cross-sectional area times L, this is the volume, times N, which is the number of charges, free charges per unit volume. So this will give me the total number of charges that are subjected. Each one of them will experience this force. So what we do, we multiply this force by this number, NAL, to get the total force. So that means the total force that this element of wire experiences is QVB crossed with B times this number, which is the number of free charges per unit volume, times the volume of the element, which is the cross-sectional area times L. Okay? So now, since the current is in the wire is given, this is what we did in the previous chapter. We said the current is N QVD times cross-sectional area. Okay? Here we have N, we have the area, and so we can and we have the Q and VD. So you can see Q VD N times the cross-sectional area. We can replace that with I, okay, and we obtain that in this case we the current I times L crossed with B. And so the remember the vector L has the length L here, and it's in the direction of the current as we have illustrated here. So you can see this is a very simple derivation of the force on a current in a wire, or a force on a wire conducting a current is given by the current I times the length vector L crossed with the magnetic field vector B. Okay, so let's take this situation here. So let's assume the length vector L has two components, one parallel to the magnetic field and one perpendicular to the magnetic field. We know the parallel component will not generate a force because V crossed with B is going to be 0, but the perpendicular component will. Okay, so in this case, when we write IL crossed with B, L crossed with B is LB sine phi, the angle phi between the magnetic field vector and the length vector. Okay, we can write this, rearrange the terms, and we can write it, it's I L sine of phi times B. L sine of phi is just L perpendicular. L perpendicular is L sine of phi. So we can write that the magnetic force that the wire experiences is just equal to the current times the vertical component, the perpendicular component of the length of the wire times the magnetic field strength. So and we can use the right hand rule to determine the direction of the force. So in this case the force is outside of the page. Okay, and so we can say that only the length perpendicular to the magnetic field, which is L perpendicular, contributes to the magnetic force. The length parallel to the magnetic force does not contribute to the length parallel to the magnetic field does not contribute to the force. It's like we did before for the velocity. We said only the perpendicular component of the velocity contributes to the force. Same thing here. Okay? Let's assume I have a zigzag. This is a wire that has this shape. So what do? I just try to determine what is the perpendicular length to the magnetic field. I don't need to measure the length of the whole wire. I just need, oops, I'm in the wrong mode. Huh? You can see it. Huh? All right, sorry about that. Okay, so you just have to determine the length, perpendicular length to the magnetic field, and you can apply the equation. So we can write that in this case, the magnetic force FB is just equal I L perpendicular times B. Okay, and again, you can see this is the direction that you can obtain. So as if we're assuming the length vector is only equal to this vector. So it's this length, and it's in this direction that is perpendicular to the magnetic field vector. Okay. So I will stop here. This is a little bit. I was hoping to finish it today, but we can do it. I hope you have a good vacation. Please send me an email with your partner. And since this is a vacation and this is producing a video, it's actually a lot of fun.